Moving on, our next speaker is Dr. Joan de Vera. Joan, like Grace, did not finish her BS or MS in NIGS, but from chemistry. However, Joan did work in NIGS and operated our ICPMS for several years. She was also an RA in our lab in EML. And Joan finished her PhD in the geosciences late last year, if I'm not mistaken, from the University of Toronto. Joan, are you there? I don't see you in my screen. And
I'm just turning on my video now.
There. Hi, Joan.
Tama po, sir.
Yes. And yeah, you can start sharing your screen. By the way, I believe earlier, Dr. Giselle Concepcion, the president of PAASE, was in our Zoom meeting earlier. I don't know if she's still here.
Are you asking me to speak for a while? Oh no.
Giselle?
Yeah.
Sure, but we hear feedback on your end.
I'm sorry because I'm on the other three sessions.
The other three parallel sessions.
Yes,
Okay,
so
go ahead.
No, I just wanted to congratulate you, CP and Bayani, to for coming up with this, you know.
Na-mute ka, ma'am. Giselle, you're muted.
Can you hear me now?
Yes.
Sorry, quickly. So two things. So first is I wanted to congratulate you and Bayani and all our speakers and fantastic attendance, including from Jun Yu Wu. And I am interested in measuring methane from a site because I have this methanotroph bacteria that is a symbiont of a rock boring shipworm, and that was published and got a lot of publicity. So actually, through one of your faculty, you're trying to look for ways to measure methane in the water and, well, of course, in the rock. And then I'm also interested in sulfur processes because we also published on a sulfur oxidizing bacterium that is a symbiont of this huge shipworm called Kufus. So that also landed in the news in New York Times and all that stuff. So I'm really very interested in your work and we really need to collaborate with geologists. So that's all I wanted to say, CP. Thank you very much for giving me a chance to speak, and congratulations to all.
Thanks, Ma'am Giselle, and of course, thank you for organizing the entire conference. It might be an opportune time to tell everyone else in this session that there are plenary sessions scheduled with very notable speakers. I think, Ma'am Giselle, correct me if I'm wrong, the one with Anne Aaron and Richard Gomez will be tomorrow?
It's July 28th. July 28th, yes. Okay? Tuesday.
CP na nakamute ka.
So I was just saying that the entire conference schedule is in the website of PAASE, paase.org. There are multiple sessions and plenary sessions scheduled today and weeks beyond. So just check that out. Maganda yung session ng plenary sa 28. Anne Aaron is from Stanford, and she's the, I believe up to now, the Chief Technical Officer of Netflix. So for everyone, FYI, we are now able to stream Netflix even in our phones because of Filipina in Netflix. That was actually part of her dissertation in Stanford. Okay, thanks again, Ma'am Giselle. We'll move forward, but do not forget, no, attention, James, Leong, and Ren, the interest of our colleagues from Ma'am Giselle's group are in the methane and sulfate reduction systems. No, so if you want to collaborate, just email Ma'am Giselle. Okay, so sorry, John, we were cut off. We can now see your slides, and you can now
Yes,
proceed.
I'm trying to put it on full screen, but I don't think the
Okay na
images are
yan.
appearing.
Okay
So I'm
naman
just
yan.
gonna present it as it is.
Okay
Kaya
na yan.
magandang umaga po sa inyong lahat. Gabi na po dito sa Toronto. So, ayun, I'm actually surprised by the huge turnout. So I understand that everyone right now is probably itching to travel. So for the next 10 minutes or so, let me take you to the Arctic and explore it through the eyes of lead and its isotopes. So this is actually part of my PhD work. And I would like to acknowledge the help of my collaborators. My supervisor is Dr. Bridget Bergquist, and so many people who helped me to finish this project. Okay. So aside from the fact that the Arctic is extremely remote, it's very cold, and I would say mysterious, scientists are very interested in the Arctic because it is sensitive to the changing climate. So they call it Arctic amplification, wherein they're observing that the Arctic is warming faster than the rest of the world. So this is nicely demonstrated in the left graph, which shows here the change in temperature between 1960 and 2011. And as you can see here, the Arctic is warming by at least 1 degree Celsius higher than the rest of the world. And in fact, it is expected that in the summer of 2040, the Arctic is going to be completely ice-free. And so these changes that are happening in the region are going to affect the biogeochemical processes. An example of this are outlined here, and all these processes are very complex. They're interrelated and unfortunately not very well understood. So one way to understand it is to look at trace element cycling because they can be part of biogeochemical processes, as I will explain in the next slide. Okay, so in this diagram, the black arrows represent the movement of trace elements from one system to another. By the way, I'll be referring to trace elements as TE starting from now. So for example, if you start with aerosols, aerosols are important carriers of trace elements, especially in remote regions such as the Arctic. And then this will be eventually deposited into aquatic and terrestrial environment. And in the Arctic, this also includes the frozen components as an important repository. And so during melting, we would expect that these trace elements will be released into the environment, including the seawater. So aside from the TEs coming from the seawater, the trace elements in the seawater can also come from shelf materials because the Arctic is mostly contains a lot of shelves. And then the trace elements can also come from the waters advected from North Pacific and North Atlantic Oceans. So these trace elements can either be nutrients or toxins for many microorganisms, and some of them can be tracers of different processes. And in the case of lead, which will be the focus of my talk, we will use this as an anthropogenic. We use this as an anthropogenic tracer. So as I've mentioned, I'll be using isotopic measurement in order to understand my research. So let me have a quick background, our discussion, and how I'm going to use isotopes in my research. So the isotopes of an element, so take for example here, the isotopes of two of the isotopes of lead, the 206 and 207, the only difference between these two isotopes is that they have different number of neutrons. And since neutrons determine the weight or the mass of an isotope together with a proton, we would expect that these two isotopes would have different weight. And if we measure this, the abundances of these isotopes in a mass spectrometer with a good resolving power, we would be able to detect this variation or fractionation depending on the samples that we're measuring. And in the case of lead, this isotopic variation is mostly due to the radiogenic ingrowth, which I will explain in more detail in the next slide. So there are 4 stable isotopes of lead, and 3 of which are actually called radiogenic. So these are 206, 207, and 208. So take note that they are stable, but they are radiogenic because they are the daughter products of the radioactive decay of uranium and thorium isotopes. And so we would expect the isotopic variation because of this radiogenic ingrowth. And so this large range of isotopic variability among samples of lead is nicely depicted in the right graph, which shows the evolution of the lead isotopes as a function of the geologic timescale. I also superimpose here some of the widely used lead ores. So for example, the European leaded gas used the Broken Hill ore, which has this characteristic isotopic compositions. And then the US leaded gas used the US Mississippi Valley ore, which has this characteristic 206-207 ratios. And so in essence, this isotopic signature, which in lead we express is in terms of ratios such as 206 over 207, can be used to fingerprint the sources. So for the first part of my work, I measured trace elements and lead isotopes in aerosols in order to identify the sources and estimate their concentrations. So we have samples taken during the 2015 GeoTraces cruise, which are depicted by the yellow dots. And we also have some samples in an alert station, which is located in Nunavut, Canada, which is depicted by the red dot here. So these are, I usually refer to this as the Canadian Arctic, just because it's very close to the Canadian country. So yeah, so here, so the first graph is simply the concentrations of lead in aerosols plotted from spring to summer. And then the bottom graph is the corresponding enrichment factor also plotted from spring to summer. So the enrichment factor is defined by this formula. And so the purpose of this is to assess the nature of the aerosols. Since we're comparing the lead to titanium ratios in the samples or in the aerosols to the lead to titanium in crustal materials, if the EF is close to 1, we would assume that the material is likely crustal in nature. For example, it comes from dust. And then if the EF is greater than 10, we can assume that it is non-crustal in nature. So there are a lot of details here, but I would like to draw your attention into the spring aerosols, which are enclosed in this red box. So the spring aerosols have the highest lead concentrations. Note that the concentrations are plotted in logarithmic scale. And also they have enrichment factor greater than 10. And this pattern is actually consistent with the Arctic haze. So Arctic haze phenomenon is a well-established phenomenon in the Arctic that happens during late winter and spring. And during this time, the Arctic is actually not so pristine because the mid-latitude pollution reaches the Arctic. And this is nicely reflected in our data set. And also, there are previous studies who have done the same thing and showing that, for example, they measured high concentrations of sulfates and other anthropogenic materials during the Arctic haze event. And in fact, during this event, the Arctic, that's why they call it the Arctic haze, because they can see all this hazy thing in the atmosphere. So the next step is to measure the lead isotopic composition of the aerosols in order to constrain further the sources. So the lead isotopic compositions of the aerosols are plotted in a 3-isotope plot, which is shown right here. So the y-axis is the 208-206 ratios, and the x-axis is the 206-207 ratios. And then the aerosol samples are depicted by the symbols. And then the solid ellipses represent the anthropogenic sources in the different regions of the northern hemisphere. And then the empty ellipses are the natural sources. So again, there are a lot of details here, but I would just like to point out that the spring aerosols, which we found to have the highest lead concentrations and are depicted by the triangles, are mostly clustered together, indicating a dominant source. And we found this to be overlapping with aerosols coming from Europe and Russia after the peak of the leaded gas. So this was measurements taken in the 2000. So again, this is consistent with the Arctic haze pattern. So the general takeaway from this project is that the anthropogenic aerosols continue to intrude the Arctic. atmosphere, especially during the Arctic haze. And this is something that is not extremely novel, but I would say that this is an important thing to do in the Arctic because as we all know, as the Arctic continues to warm, it's going to attract a lot of local anthropogenic activities. One thing that I can think of is mining. So the Arctic is very attractive to mining. In fact, a lot of countries have already taken their stake in the Arctic, including China. And another interesting another interesting activity there would be the shipping, because the Northwest Passage is the more straightforward route between North Atlantic and North Pacific Ocean. So once I think they've already started it, and once the Arctic becomes completely ice-free, it would be a favorable route for this shipping lines. Okay, so for the next part, we wanted to find out if the anthropogenic lead that we found in the atmosphere can also be found in the Arctic seawater. So some of the backgrounds or information that we know before that we kind of figured out before we started this project is that the concentrations of lead in the Arctic are generally very low compared to the other ocean systems such as Pacific and Atlantic oceans. And then based on proxy measurements, it was kind of assumed that the Arctic might still be pristine. So in order to find out if the Arctic is indeed pristine, we measured the lead isotope compositions in the seawater. So we measured it from filtered seawater, so we refer to it as the dissolved lead isotopes. And we have samples taken in Canada Basin, which is right here. I don't know if you can see my cursor here. So Canada Basin is one of the 4 basins of the Arctic Ocean. And then we have samples from Canadian Arctic Archipelago. So the Canadian Arctic Archipelago is an important link between the Pacific Ocean and the Atlantic Ocean, because the Pacific water enters here, and then the Arctic water goes through here and enters through the Baffin Bay and then exits to Labrador Sea, and then the Atlantic Ocean is south of the Labrador Sea. And then the Baffin Bay is the one that is north of Atlantic Ocean. So the samples that we've measured are depicted by the symbols, and then we have samples measured from surface to the deep water. Okay, so this is the same plot that I presented before, only that I've added the isotopic compositions of the Arctic seawater, which are represented by these different symbols. So for Canada Basin, they are right here. And for Canadian Arctic Archipelago, these are the diamond symbols. And for Baffin Bay, there are the square symbols. So there are many, you will notice that many of the data points actually overlap with the anthropogenic sources, which tells us that indeed anthropogenic lead is found, if not pervasive, in the Canadian Arctic. Another interesting finding that we found here is that if you look at the 206-207 ratios, the lowest 206-207 ratios, those that have values less than 1.15, which are right here, actually overlap with historic lead input, which we think came from European leaded gas and Russian smelters. Both of these are the only possible sources of low 206-207 ratios in the past. And another cool thing about this is that if you look at the concentrations, these low 206-207 ratios are associated with the highest lead concentrations that we measured in the water column, which leads us to suggest that the historic Eurasian lead, those that came from European leaded gas and Russian smelters during the 20th century, is an important source of dissolved lead in the water column of the Arctic. Okay, so far we've established that the historic Eurasian lead is an important source in the water columns. So the next question that we wanted to find out is how did this historic Eurasian lead reach the Arctic? So one route is through direct atmospheric deposition. But then you also have to think about the other possible source, which is the waters that are advected from North Pacific and North Atlantic Ocean. Both of these ocean systems are heavily influenced by anthropogenic lead, especially during the leaded gas emission in the 20th century. But then, as you can see in the left graph, the isotopic compositions of the North Pacific Ocean and North Atlantic Ocean cannot be the source of this low 206-207 ratios, which are right here, because they have much higher concentrations. So these kinds of support our hypothesis that this historic Eurasian lead are brought to the Arctic via atmospheric deposition. And this is also supported by the Arctic ice core records measured in the Arctic, which can be used as an atmospheric proxy. As you can see here, the lowest, so as you can see here, these ratios right here also correspond to low to 6 to 7 ratios. And so which and this correspond to the emissions in the 20th century, which kind of support our hypothesis that aerosols are brought to the Arctic, specifically this historic Eurasian led via atmospheric deposition. So to conclude, first, we found that anthropogenic aerosols from Eurasia continue to intrude the Arctic's atmosphere. And then second, anthropogenic lead is present in the Canadian Arctic seawater with significant contribution from historic Eurasian lead aerosols. And I forgot to mention that one important implication for this is, of course, something to do with the warming of the Arctic, because as it warms, it is possible that all this previously deposited aerosols, especially those that were emitted during the high lead emission in the 20th century, may be remobilized and can be further observed in the water column. So that's about it. So what's next for me? I'm really interested in isotopes, so I'm hoping to still measure the iron isotopes in the same water samples in order to understand the biogeochemical cycling of iron. And as part of my postdoc right now, I'm trying to switch gear from the ocean to groundwater, wherein I'm looking at groundwater contaminants using compound-specific isotope analysis in order to understand the sources and fate of this contaminants. And also, I'm a little bit challenging myself and learning about reactive transport modeling to be able to help further with the interpretation. So that's about it. Maraming salamat. And I'm just gonna leave you with this very moving photo of what's happening in the Arctic right now. There are so many things that I can tell you about why we should care about the changes in the climate, especially with the warming of the Arctic. But I think this hits home because, as you can see here, this polar bear is going to have a very difficult life going forward because they use the sea ice in order to have a wider forage area. But now that since these are melting, like they're really having a hard time moving from one place to another. So that's about it. Thank you very much.
Thank you, Joan. I think what you mentioned earlier, and it was my first time to realize that, is that the lead aerosols coming from the early 20th century emissions from Europe and Russia are still the same contaminants being observed in the Arctic. At least
yes,
dominant. And my next question is, what about the emissions from more recent sources like China? Konti lang ba sa Arctic yun?
I think the reason why we're observing the dominant, the influence from Eurasian during the, like for example, the leaded gas is because these are really high concentrations compared to the one. So actually the China thing is, there are studies in some parts of the Arctic wherein they're seeing Chinese aerosols. For example, there are some Greenland studies. And So I have some samples here that kind of overlap also with the Chinese aerosols. These are for the Arctic aerosols that I've measured in more recently. But I'm not sure if this is exactly coming from China, because this also overlaps with the Arctic sediments, with the Russian Arctic. And I kind of coupled this with I'm forgetting the term now, AMB, like air mass back trajectory analysis, and I'm not seeing the pattern coming from China. But I'm not completely ruling it out because some studies said that they found the influence from China.
That's great. Thank you, Joan. And when you start your research on isotopes in groundwater, make sure to connect with Bayani. No, expertise ni Bayani yan.
Sige po, kailangan ko siyang tulong sa reactive transport modeling.
Bahala ka na, Bayani. All right, thanks, Joan.
Thank you, sir. Thank you, everyone.